BGP is the protocol of the internet for a very specific reason, and it comes down to BGP design. You see, BGP, like I've said, is a very deliberate protocol. It behaves exactly like how we tell it to. It doesn't try to figure things out dynamically on its own. And what this really boils down to at the end of the day is we have a tremendous amount of administrative control over how BGP operates or behaves. Now, as an enterprise, what we're focused on is how we connect to ISPs and share our routes to each other. So what we need to do for this particular nugget is talk about how an enterprise would be designing its BGP layout. How would we load balance traffic going out of our enterprise? How would we handle traffic as it comes into our enterprise? And how do we stop traffic from turning us into a transit network? That's going to be a big thing to talk about as we end this particular skill on BGP design. So get ready, because this is going to be a lot of fun as we apply our BGP skills to actual enterprise design considerations when we have single ISPs or dual ISPs, and how we handle traffic going out as well as traffic coming in. Let's get going. So we're operating a large enterprise network, and what we've done is we've actually acquired public IP address space for ourselves. Our enterprise has its own public IP address space so that we can host our own applications or services for the world and the internet to find. The next thing that we have to do, though, is tell the internet about this IP address space, and this is where we as an enterprise start peering with service providers and advertising our routes to them. So what we're going to set up in this particular nugget is what happens when we have a single ISP but maybe a couple different uplinks. That way we can manage how traffic is allowed to flow outbound towards our ISP. Let's get going. So this is going to be the basic topology that I'm going to be working with as we explain BGP design. And as we change things up and go from one ISP to two ISPs, we're going to be changing up the topology a little bit, or at least the design here, but the overall flow of it is going to feel the same. Here's how it works. In the red section here, this is our enterprise. This is our business that we're managing, and this R1 right here is our edge router that goes out towards the internet. Now, we've acquired this public IP address right here, 200, 200, 200, 200, and that's what we're trying to advertise out to the world. Maybe behind it there's a server or something like that, a web server that's hosting our website, and that's how people find us. So we need to form a BGP relationship to our ISP. That way we can actually not only advertise our public address space out into the internet, but also so that we can get out to the internet, so that we have outbound traffic going out towards the internet too. So that way people out in the internet can come into us, and then we can go out to the internet, and you kind of get the idea. That's the basic flow here. So we've partnered with an ISP here, and the ISP has given us a redundant uplink towards the internet with two redundant routers looking like this that are located in R3 and R4. And then behind that is the actual internet itself. Everything goes out to the internet from there. So this is kind of the basic setup that we have here. We're going to be using, oh, a little typo here. I'm going to fix that right now. There we go. Sorry about that. We're going to be using BGP Autonomous System 100 for our enterprise, and the ISP that we're pairing with here is BGP Autonomous System 200. Now, since we've already talked a lot about configuration and how BGP works and the flow of things up to this point, I've already taken the liberty of configuring BGP. There's an iBGP relationship here between R1 and R2, and then there's eBGP relationships between R1, R3, and R4. There's also an iBGP relationship between R3 and R4 on the ISP side of things. Let's bring up the console and take a look at it real quick. Here I am on R1. If I give it a show IP route real quick, we can see that we do have some BGP learned routes here. First of all, we have the iBGP learned route down here from our neighbor, giving us 200, 200, 200, 200. But then we also have a default static route coming from our ISP, as well as a BGP learned route here, 10, 10, 21, 1. And we see that we're choosing to go through the R4 route at this time. I can actually go into show BGP IPv4 unicast, and sure enough, I see that this route was advertised to us from router 3 as well as router 4. But here's the thing, they're equal cost paths to get there, but BGP's default behavior is to only choose one winner, one route towards the destination. Now, just so for your reference, that subnet is right here on both of these devices, right here. There's basically a layer 2 switch connected between them like this. So why is it that R1, in order to get to that network, only chooses one path? In this case, it's actually choosing to go through R4 when it could actually load balance this traffic across them. That's just how BGP's default behavior works. And in a situation where we actually want to load balance our traffic out here, what we need to do is we need to configure our BGP instance to allow more than one path. This is as simple as setting the maximum paths setting. Check this out. My end goal here is to actually allow multiple paths to the 10.10.21 network. So what I can do is I can go into configuration mode, I can go into router BGP, my autonomous system, which is 100, and then I'll go into my IPv4 address family. All I have to do is set maximum paths and then say, how many maximum paths will I allow installed and load balancing across? In this case, I only have 2 paths, so I'll just say maximum paths 2. I'll exit out, and what I'm going to do is I'm going to do a soft reset, so that way we actually bounce the traffic and reload our BGP table and routing table from traffic that's coming from and advertised from AS200. There we go. The administrative reset is taking place in the global VRF. If I give it a show IP route now, I got to spell IP correctly. Check that out. Now you can see we have 2 routes installed in the routing table for load balancing across the. If I also give it a show BGP IPv4 unicast, we can actually look at the BGP table itself. And now we've got this cool little M denoted here saying that this is a multipath allowed for load balancing. So that's how we could actually set up a situation where we allow for load sharing outbound traffic to one single ISP when we have equal cause multipaths. It's just as simple as setting the maximum paths. Now we know that we can actually do load balancing towards one ISP that has 2 redundant uplinks. I hope this has been informative for you, and I'd like to thank you for viewing. Now, in the previous nugget, we set up the scenario about how we're going to handle a situation when our enterprise has 2 uplinks, a redundant uplink, to a single ISP, and how we want to balance traffic as it flows outbound and traffic that's advertised into us. We saw how we could use the max path setting in order to actually allow multiple paths outbound towards the internet. But a more common scenario in an enterprise network is when we're going to have 2 ISPs, a dual-homed router or a dual-homed enterprise. How would we then balance traffic as it goes out of our enterprise that way? This is where BGP gets a little more restrictive because we don't have an automatic load balancing situation. What we really have to do here is do what's called load sharing, and that's what this nugget's going to be all about. So let's talk about how load sharing works in BGP with a dual-homed ISP situation. Now we've changed up the diagram a little bit to talk about what happens when we have 2 separate autonomous systems or 2 separate ISPs. And what we want to do is we want to have, again, a flow of traffic going out both links towards the internet. This is where BGP becomes a little bit more restrictive, because in the last situation where we had a single ISP, we could enter the max paths command or maximum paths command, and it would automatically do the equal cost load balancing or equal cost multipathing for us. That doesn't work when we have advertisements from different autonomous systems. Basically, it works in eBGP when we have advertisements from the same autonomous system, but in this case, when we have an advertisement to, say, the 10.10.21 network coming from Autonomous System 200, and then the 10.10.21 network coming from Autonomous System 300, we can't use max paths in this case because BGP's default behavior is to pick one of them. It's to pick one outbound prefix. So here's the situation. There's no real way that we could load balance towards that one prefix using BGP. However, we can do stuff. We can still load balance, or load share, I should say, our outbound traffic towards the internet. And this is how we actually rig this to work. We would actually set up prefixes that match traffic from basically 0.0.0.1 through 127, 255, 255, 255, and we would allow that traffic to go outbound towards this specific eBGP autonomous system. On the other side, we would say 128 through the max of, 255, whatever, would go out this specific prefix. That's really the best way that you could handle outbound traffic sharing when it comes towards multiple eBGP neighbors. Now, that's really it. That's how you handle an outbound situation with multiple ISPs, is to simply set up prefix lists or access lists that match the first half of all of our available traffic, of our first half of our 32-bit range, and then the second half of our 32-bit range, and allow that traffic to go outbound towards the peers like so. It would obviously help to have multiple routers and redundant uplinks with similar access policies in place. That way, if one of these links goes down for any reason, our IGP would then be able to reroute traffic out towards that direction too. So this is a situation here where in our diagram, we only have one router, but in order to make this really work with multiple ISPs, we still have single points of failure all over the place, and this would eliminate half of our internet-bound traffic if one of these links were to go down. So that's why we would ideally have a second router set up here with an IGP set up to identify when one of these links or track one of these links that goes down, and then we would use something like this to get the traffic outbound that way. You could even use something like VRRP in this particular link right there in order to help distribute that traffic that way. So that's been understanding how to handle outbound traffic when we have multiple ISPs. I hope this has been informative for you, and I'd like to thank you for viewing. So up to this point, we've talked a lot about how traffic flows out of our enterprise and out into the world, and that's obviously a very important thing to consider. But also think for a moment, what was the entire point of us getting that public IP address space in the first place? It was so that traffic that originates from the internet could come into us. And now we have a situation where we need to control how traffic flows inbound, maybe from one ISP or from two ISPs. In this nugget, what we're going to talk about is how we can control traffic as it flows inbound from a single ISP, but maybe with a couple redundant uplinks. Let's get going talking about that situation. Remember, we are advertising the 200, 200, 200, 200 prefix towards this ISP, and it gets advertised towards both of these routers. There could be a situation, though, where we only want traffic to arrive inbound on one specific interface as opposed to from both specific interfaces. So what we can do is we can now use some sort of way to manipulate how traffic comes inbound towards this specific prefix. One of the most common ways to manipulate how traffic comes inbound from a specific autonomous system is to use the MED, or the multi-exit discriminator. A lot of people call it the BGP metric. In this case, the way it works is we're going to advertise the prefix towards both of these devices, but we're going to give them a different metric. That way, one of these metrics will be preferred over the other, as these two routers start communicating about what they know about it. Just like other metrics in other IGPs, the lowest metric is going to be preferred. It's kind of like the lowest cost or the shortest distance or something like that. So if we were to advertise a MED out this prefix or out this link right here with a 10 and a MED out this link here with a 100, their autonomous system will communicate about this route, and it'll decide, oh, the MED with 10 is the best way to get into this autonomous system. Now, if anything happens to this link whatsoever, there still is a backup advertisement here, and it'll use the 100 to do that. Now, configuring the MED in this particular series, in the design series, is outside the scope of this particular exam. You don't need to know these configurations. But I did want to at least show you what it looks like and how it works. You don't have to know these commands, but it does help to actually see them in action and see how this behavior actually works. So what we're going to do is we're going to start over here on R1, and I've already brought the configuration commands up here. We're going to start right here with the access list. You can see the first thing I'm doing is I'm matching the 200, 200, 200, 200 host address right there. Within that access list, once I've matched the address, this is where I can choose to actually set the metric using the route map. I've identified two route maps here. One is going to be setting the MED for our neighbor relationship to R3. That's the 13 prefix. I've also got a route map here that sets the relationship between R4. That's the 14 prefix. You can see what we've done on this particular screen is the relationship to R3. I've set the metric to be 100, and the relationship to R4, I've set the metric to be 10. 10 being the more preferred of the two. traffic should enter then from R4. So up here in the BGP configuration, this is where I actually set it. Under the IPv4 address family, we tell it under the neighbor configuration, right there, the neighbor, we're going to be using the route map for the MED13. We're applying that metric as it goes outbound. Same thing with R4. We're specifying the route map, MED14, as it goes outbound. So as traffic gets as this prefix, the 200, 200, 200 prefix get advertised towards R3, the MED13 route map is going to set the metric to 100. And as the 200 prefix gets advertised towards R4, or the MED14, the 10 metric is going to be advertised towards R4. So our expected behavior is that traffic should then, let's go back to this, meet our qualifications here. The MED of 100 gets advertised this way. The MED of 10 gets advertised this way, and therefore this autonomous system should prefer to go this way as it enters our autonomous system. So with those applied, let's jump over to R4 first. Let's see and verify with a show IP route. Sure enough, right there, I see right there the 200, 200, 200 is going back towards us, the 114.11. And what I should expect to see is on R3, if I give it a show IP route, sure enough, there we go, right there. The traffic is not going out that public IP address. It's traversing the internal address towards R4 before it then goes out towards R1, which is our autonomous system. I can also give it a show BGP IPv4 unicast to look at the BGP table, and sure enough, this is the big thing right there. We see the metrics that are advertised, and the winning metric is going to be the lowest metric right there. So that's how we can manipulate inbound traffic coming from a single ISP that has two uplinks. We can use the MED to say, prefer to come in on this interface as opposed to that interface. I hope this has been informative for you, and I'd like to thank you for viewing. So in the previous nugget, we set up how we could control inbound flows when we have a single ISP but dual uplinks. Now let's talk about, again, the more real-world scenario where we have two ISPs. We're a dual home situation. How would we handle traffic as it flows inbound? Maybe we have a preference that traffic comes in from one ISP than the other. That's what this nugget's all about. Let's get going talking about how to handle inbound flows when we have two ISPs. We're going to have a lot of fun with this one because this is also another one of those situations where the previous solution, when we had a single ISP, isn't going to do the trick. The entire point of the MED was so that a single autonomous system could choose a path that's coming in with a better metric. But if this device right here is going to be advertising a MED of 100 towards that direction and a 10 in this direction, guess what? That's where the buck stops. This device here in Autonomous System 300 still only sees a single entry point here, and R3 still only sees a single entry point here, and it won't be able to use the MED to distinguish a better way to enter the entire autonomous system that we have. So what we need to do is we need to make one path seem less attractive than the other paths, and this is where we can actually pre-pinned autonomous systems onto our advertisement itself. Think about how the default BGP path selection works. If all else fails, the shortest AS path is going to win. So what we can do is, as we advertise towards R4 here in autonomous system, let's say that's the one we want to win. Let's say we want traffic to enter through autonomous system 300. We'll leave it untouched. That way R4 sees that the path to get into the 200 prefix here is through autonomous system 100, and there's only one autonomous system away. As we advertise traffic out towards R3, though, we have to make it seem less attractive. So what we can do is, when we advertise our autonomous system 100 as the next path, we could actually tack on multiple 100s, so it looks like it has to go through 4 autonomous systems in order to get there. Now again, configuration is not a major part of the ENSLD playlist, but here is how it actually looks in action. If I bring it up. On R1, I've gone ahead and I've identified an access list that matches the 200 prefix that we're going to be advertising. Then I've created a route map right here that you can see we've set the AS path to pre-pinned 100, 100, 100, and then our advertised 100 will come on the end of that. So we should see 4 100s as the path that we're going to be setting here. Now here under my BGP configuration for router 3, I've tacked on this route map as it goes outbound. So that way it tacks on the AS path prepinned as it goes outbound towards R3, and R4 I've left completely alone. If I jump over to R3 real quick, I'll give it a show BGP IPv4 unicast, and we'll look right there. Do you see what happened? R3 now sees that we've tacked on 100 3 times in front of our initial advertisement, whereas the AS from 300 advertises only 2 paths that it needs to hop through. So guess which one wins? The path through R4. If we look over on R4 real quick, let's give it a show BGP IPv4 unicast. And sure enough, it only sees right there the best path forward is going to be through 100 because we didn't advertise or prepend any of the paths onto it. So we can manipulate how traffic flows inbound into our autonomous system with multiple ISPs by simply prepending our own autonomous system onto it multiple times so that it looks less attractive to one other external autonomous system. I hope this has been informative for you, and I'd like to thank you for viewing. One of the most common scenarios that you run into when you have 2 ISPs is the default behavior of BGP. As our ISPs advertise traffic to us, guess what happens? The default behavior is to advertise that to our other eBGP neighbors, which means we're going to be advertising routes to our secondary ISP, and this creates a problem because we could then become a transit network for the entire internet doing something like that. That's going to be a big deal that we need to shut down. We're going to talk about this a little bit more and how this flows, but what we're really introducing in this nugget is communities. That way we don't transmit information from one ISP to another and we don't end up becoming a transit network. Let's get going talking about how we could stop the advertisement of traffic from one ISP to another. Well, now we've got ourselves into a situation. Let me set up what's going on here. Recall that this link on each of these interfaces was the 10.10 21.0/24 subnet, and both of these devices were advertising this prefix down to R1. What I've done now is I've had a situation where this link has gone down and this link right here has gone down. So R3 has lost its knowledge of the 10.10 21 subnet because it's no longer directly connected. But think about the behavior of BGP. When an eBGP advertisement comes in for that prefix from R4, R1 learns about it, and then guess what it immediately does? It immediately punts it back out to other eBGP neighbors. So R3 is like, oh, wait a minute, I still know how to get to this prefix because this autonomous system 100 is advertising it to me. And now our enterprise grade router has become a service provider network because this service provider here is now using our router to transit in our autonomous system to transit through in order to get to the 10.10.21 network. Check it out. Here's how it looks right now. I'm starting off on R4 and I'll give it a show BGP IPv4 unicast, and we can see it knows exactly about the 10.10.21 network, and it is the advertising router. That's the 000 next hop. If I jump down to R1, I'll give it a show BGP IPv4 unicast to look at the table, and sure enough, it knows about the 10.10.21 network because it's learning about it from R4. Now again, the eBGP relationship and the eBGP neighborship is such that when it advertises out towards a new eBGP neighbor, it will update the next hop to be itself. So when I jump over to R3, where those interfaces are all shut down, and I give it a show BGP, got to type it correctly, IPv4 unicast, look at this. Now it's learning about the 10.10.21 network from our router, R1. It sees that the path is going through AS100, and our enterprise network has now become a transit network, and this is a big problem that we need to shut down. Now, there's a bunch of different ways that we could solve this issue. The manual and difficult way would be to do things like setting up prefix lists or distribute lists and filtering it out as it comes outbound. We would have to do this for every single prefix that we learn from an ISP, and this would become very administratively complicated to learn and to do. The better thing that we can do is use something called BGP communities. Now, BGP communities are a huge topic. because we can really use them for a bunch of different ways, but there's some main communities that are well known throughout the world. The first one, and the one that we'll talk about that solves our problem, is the no export community. As we advertise a route outbound, we can tack this community onto the end of this route that says, don't export this to other autonomous systems. Similarly, we can add the community on as the route comes inbound. So as R4 advertises this route, R4 could either advertise it with the no export community tacked onto it, or we could add the no export community onto it as it comes into our autonomous system. That way, our router knows we're not allowed to export this prefix outbound to another autonomous system. We can still advertise it down here towards R2 because it's within our autonomous system. The no export community is basically additional functionality that says don't export this to other eBGP neighbors. There is also the no advertise community, which literally stops it from being advertised at all. If R4 were to set the no advertise community, or if we set it inbound as it comes into R1, we would not advertise it towards R3 or towards R2. There's also the local AS community, which says that we can only advertise this within our local autonomous system, and this is largely used in confederation. For instance, if AS100 were broken down into even smaller autonomous systems, we could use local AS to keep it within our local autonomous system rather than advertising it throughout the confederation. Lastly, there is the internet community, which says that this prefix is really only bound and usable for the internet. Now again, the thing that we want to focus on to stop our router from becoming a transit router is going to be the no export community. Now we could either ask the ISP to set that community as it goes outbound towards us, or the easier way to administer this is to actually set it as it comes inbound. So any advertisements that R4 is setting towards us, we can set the no export community on it as it comes inbound. That way we won't export it towards R3 in this case. I've already done a lot of the prep work for us on R1. On R1, if I give it a show run, we'll just look at the access list real quick. We can see the first thing I'm doing is I'm going to match any prefix here at all that comes inbound from R4. So my access list just matches any prefix at this point. We're not actually using it until we start using it in a route map. So from here, I'll run show run section route map. And here I see I'm matching all prefixes, and I'm setting the community to no export. We're going to apply this to our neighborship with R4 as it comes inbound. So let's get that going real quick. I'll go into configuration mode, router BGP 100. I'll go into my address family for IPv4 unicast, and my neighbor that is 100.14.1.4, I'm going to set a route map that was community inbound. Real quick, I'm going to bounce my neighbor relationships between all of my devices. So I'll bounce the 300 autonomous system first. That way it actually sets the community. Then I'll bounce the 200 relationship. That way we will not export this towards AS200. If I jump over to R3 real quick, we can see this is what it looked like before, where I was exporting this, and we can see it right here. Now when I give it a show BGP IPv4 unicast, we should expect that all of the learned routes from Autonomous System 300 have the no export community set on it. But we didn't set the community on our own internal routes that we learned about. So when I run this command, there it is. We've now stopped our autonomous system from becoming a transit autonomous system using the no export community. I hope this has been informative for you, and I'd like to thank you for viewing. If you're following along in this ENSLD playlist, or the ENSLD playlist as we like to call it, you are no doubt learning about route reflectors and how we've used route reflectors to solve some iBGP scalability issues. But route reflectors, well, there's more to it than meets the eye. And we actually need to talk about how we could design a route reflecting network, where it really fits in to our enterprise network and how route reflection should work. We need to consider things like scalability and stability. This is going to be talking about redundancy as well as the ability to expand our actual network and how networks are shared throughout our iBGP topology. So in this particular nugget, what we're going to do is we're going to recap why we need route reflectors in the first place, what problem do they solve, and then talk about how we could step our route reflector skills up a notch when we consider how we lay out our route reflectors through our topology. This is going to be covering things like clusters or no clusters or different clusters, or should they even peer in the first place. Really, really fun stuff as we get started talking about route reflectors. Let's go. So I've written the objectives of this particular nugget on the screen because, quite frankly, this is going to be a pretty big nugget. Route reflectors are a critical part of almost every BGP network. And why do I say almost every BGP network? Because almost every BGP network has to adhere to a general rule of thumb of when to use route reflectors. Now, this is not a law. This is not part of an RFC. This is not a requirement. It's just a rule of thumb. And what is that rule of thumb? If you have an iBGP environment that uses about 4 or more routers, it's time to start introducing route reflectors into that environment. So we've already talked about one of the very first things in this particular nugget, and that is the route reflector rule of thumb. So it's not uncommon to have iBGP running in an enterprise or especially a service provider and have route reflectors. Route reflectors are going to be there because really, as soon as we start getting 4 or more routers, we start introducing the usage of route reflectors. Now again, why is that? Why do we need route reflectors, and what problem do they solve? Why is it that when we have 4 or more? It all comes down to bullet point number 2 here. This is the iBGP full mesh formula. Recall the behavior of iBGP. This is a big thing about iBGP. A loop prevention mechanism of iBGP is that when a route is learned from an iBGPer, like between R3 and let's pretend R4 here, these two are sharing routes back and forth to each other, R3 will not forward that prefix to other iBGP peers. Even further so, if it did, it wouldn't set the next hop to be itself. It doesn't change the next hop itself. So in order to get connectivity throughout my entire enterprise without doing anything else, we would have to have a full mesh of connectivity so that the routes that are exchanged between R3 and R4 are also exchanged everywhere else. So in this case, we would have a connection between R4 and R3, R4 and this reflector 1, R4 and this reflector 2, R4 and R1, and then R4 and R2. And then R2 would have this connect. Do you see where I'm going with this? This connection would look something like this. And it would become a very big scalable mess that we have here. So that's why they introduced route reflectors in the first place, was to help us scale and not need that full mesh connectivity. If you're curious when this would really come into play, this comes into play when we have large enterprises, again, with 4 or more iBGP prefixes or iBGP speaking peers. But the formula looks something like this to calculate how many iBGP sessions would be in existence or need to be in existence in order to create a full mesh. The formula is the number of iBGP peers times n-1 divided by 2. Now, again, this kind of gets mathematical. We have the order of operations. I remember this as, please excuse my dear Aunt Sally. That's parentheses. So everything in the parentheses is handled first. Then everything with exponents is handled next. We don't have any of those. Multiplication, so that would be this right here. And then division, then addition and subtraction, which we have almost none of. We just have this subtraction right here. So the formula really looks something like this, where we have n minus 1 is calculated first, then it's multiplied by n, then it's divided by 2. So let's pretend for a moment that we had something like 1,000 routers in our large enterprise. Maybe it's a global enterprise or even a service provider network. If I bring my calculator into the screen, I'll just hide my text for one moment. We'll take those 1,000 routers. So real quick, if I write on the screen, the formula would look like 1,000 times 1,000 minus 1 divided by 2. I can just eyeball that 1,000 minus 1 and say it's 999 right now. So if I write 999 right here, we really have 1,000 times 999 divided by 2. I could literally type it in like that. So with my 1,000 routers to achieve a full mesh of connectivity with iBGP, it would look like 1,000 times 999 divided by 2, we would have 499,500 TCP 179 or BGP sessions established in this environment. Yikes, huge stability problem right there, as well as scalability problem. We won't be able to expand further very easily now, would we? Beyond that, this would require an absolutely massive router to make this happen. So this is the problem that route reflectors solve. It introduces a mechanism for allowing routes to be shared from one iBGP peer to another iBGP peer by bouncing these routes off of one designated router. The idea is that these route reflectors that we've designated here in this particular network as Reflector 1 and Reflector 2, they would know who of their peers are their route reflection clients, and they would then know where they should bounce or reflect routes off of. Recall the route reflector rules of when routes get propagated or shared throughout the network. In our example that we're going to be talking through in this particular nugget, let's say our enterprise, CBT Enterprise, has the autonomous system number 200, and we are going to be peering with a service provider network. Now, of course, we're going to be sharing routes towards the service provider, but that's not really what this nugget is all about, or the use case of the route reflectors in the first place. In this case, let's say the service provider network is advertising this route 1234 to us. This advertisement will be learned via eBGP, correct? And eBGP routes are then shared to our iBGP neighbors. In this case, R1 only has two peers. That is Reflector 1 and Reflector 2. Now, we're going to get into why are there two route reflectors in just a moment when we start talking about redundancy. Right now, we're just refreshing the behavior of eBGP versus iBGP. The idea that we want here in this particular scenario is that we want this prefix 1234 to be propagated throughout all of my enterprise, which is, of course, an iBGP establishment. These are all speaking in ASN 200. So the route reflector would then bounce this route to all of the other routers so long as R1 is a known client. Routes that are advertised from a client will always be propagated towards clients or non-clients. So as long as we configure Reflector 1 to say that, hey, R1 is a route reflector client, it'll bounce the routes that it learns from R1 to the other adjacent routers that it has. So in this case, because we only have the one eBGP relationship, we'll only learn about external prefixes through R1, and Reflector 1 could set up that R1 is its client, and by default, it would send the learned prefixes from R1 to all of the other routers in the environment. Now, of course, if we expected to learn routes from R3, R4, or R2, then we would want to set them up as clients as well. Because routes that come in from non-clients will only be forwarded to clients at that point. So if R2 was not a client, and it shared a route towards our reflector, it would only be sent back to R1, unless R3 and R4 were also configured as clients. So this refreshes how route reflectors work, and now we can transition into our design considerations when it comes to route reflection, especially when we're learning of a prefix like 1234/32 from our eBGP relationship. The first thing we need to talk about is redundancy. This is going to add stability into our network. As you can see, and we've kind of hinted at it already, we have two route reflectors in our environment. Now you can see that each one of these routers right here is peered next to them. So R1 has a connection to Reflector 1 and Reflector 2. R2 has a connection to Reflector 1 and Reflector 2. R3 has a connection to Reflector 1 and Reflector 2. And R4 has a connection to Reflector 1 and Reflector 2. So let's pretend for a moment that the service provider advertises their prefix in through R1. When we have two reflectors in our environment, and on both of these devices, we've configured R1 to be a client. I'll type it over here real quick so we know it's a client. R1 is going to advertise its prefix, its eBGP learned prefix, towards Reflector 1 and Reflector 2. And both of these devices will reflect these routes towards all of the other peers that it has. So Reflector 1 sends its learned route to R2, 3, and 4, and Reflector 2 sends its learned route to R2, 3, and 4. This is already a huge talking point when it comes to stability and scalability because we now have redundancy in place. If for any reason the connection between R1 and Reflector 1 goes down, guess what? We're still learning about the advertised prefix through Reflector 2. But since we have two route reflectors, this then begs the question that we should talk about, and that's bullet point number 4 here, is route reflector clustering. Clustering is a big deal when it comes to route reflection because the larger our enterprise grows, we're going to set up pockets of redundancy and route reflectors throughout our enterprise or throughout our HQ. So what we would do here in this particular scenario is we would define a cluster between our reflector 1 and reflector 2. But notice one critical point of this particular diagram when I clear the screen here, and that's that reflector 1 has no direct peer between reflector 2. So let's consider a big troubleshooting point that you may run into if this is how your topology is laid out. If R1 learns about this prefix 1234, and it's an eBGP learn prefix, and its link to reflector 1 goes down, we're still okay because the reflector 2 link is up right here. So reflector 2 would then bounce the routes back to R2, 3, and 4. But now what happens if the link between reflector 2 and R4 goes down? Because reflector 1 never learned about the route, and therefore it never reflected the route to R4, and the link between reflector 2 and R4 went down, R4 here is just out of luck. And luckily for us, the solution to this problem is pretty stinking easy. All we have to do is set up a peering between our reflectors. So if I just draw it on the screen right there, look at that. Now we've got the connection set up between reflector 1 and reflector 2, and that's right, reflectors still reflect to other reflectors, especially if they're clients, but still not if they're not. So in this case, if the connection between R1 and reflector 1 goes down, and the connection between R4 and reflector 2 goes down, look at how this path would still be advertised. It would go from R1 to reflector 2, then reflector 2 would advertise it to reflector 1, and then reflector 1 would advertise it over to R4. That's pretty cool, right? Now we've introduced stability and redundancy and scalability in mind. We now have a way to manage route reflection throughout the entire network with redundancy in mind, as long as we keep the peering between route reflectors up. But this then begs the question about how route reflection would work whenever there's clusters involved. Remember, clustering is a pretty big part of the BGP best path selection algorithm. Clustering is the ability to define when route reflectors should work together and advertise different best paths within a particular network. It looks something like this. Let's pretend for a moment we tell the reflector 1 device here that it belongs to a route reflector cluster of 1.1.1.1. Let's tell reflector 2 it belongs to the same cluster of 1.1.1.1. R1 is going to learn again about the 1234 prefix via eBGP, and it follows the same behavior as it always does. It's going to advertise 1234 to reflector 1 and reflector 2. Reflector 1, upon receiving this prefix, sets an attribute on this prefix, and that's that it belongs to cluster 1.1.1.1, and its originator is R1, or really what would be the router ID of R1. R1 also advertises that same prefix to cluster 2, or reflector 2, who then sets the attribute of cluster 1.1.1.1 and originator of R1. The route reflectors do what they've always done, and that's forward this information to its client devices. So reflector 1 will send this to R2, 3, and 4, and reflector 2 will send this to R2, 3, and 4. And that's all well and good. But the big thing and the real magic happens right here, and that's this link between the peers. When reflector 1 receives this and it sets these attributes, it then forwards this over to reflector 2. And reflector 2 will look at this advertisement coming from reflector 1, and it sees that it's got its own cluster ID and the same originator ID that it has when it received the prefix. So what it does is it drops the advertisement. Big talking point right there is that it drops the advertisement because it sees that this is already working in its particular cluster. But it does also turn around and sends an advertisement back to reflector 1. Reflector 1 follows the exact same behavior. It sees that it's already a part of the same cluster and it has the same originator ID, so it drops the advertisement from reflector 2. This is a big talking point about when we have the same cluster and the same prefix and the same originator all comes in the same environment. There's a lot of sames in that sentence, isn't there? That's how it's going to behave when these devices are in the same cluster. But now let's consider for a moment, let's say we put reflector 1 in cluster 1.1.1.1 and reflector 2 in cluster 2.2.2.2, and there is a peering relationship between these route reflectors, and they're both clients of each other. The same thing happens again, where the advertisement comes in from the service provider, and R1 advertises it towards reflector 1 and reflector 2. But now the behavior changes a little bit. Reflector 1 sets the cluster attribute one more time to be 1.1.1.1, and the originator is R1. But reflector 2, when it receives this, is going to set the cluster equal to 2.2.2.2, and the originator is going to be R1. Now when R1, or when reflector 1 has this attribute already set, it's going to advertise this towards reflector 2, and this is where it gets kind of cool. Reflector 2 looks at this and says, wait a minute, this is different from what I have. I have a different attribute set in my environment. So the first thing it determines is that this is coming from a different cluster. This is a different path to get there. And it evaluates the path that it would have to go through. From reflector 2's perspective, this advertisement from reflector 1 would have to traverse through cluster 1.1.1.1, then 2.2.2.2. Or it would look at its own table that it has when it received the route from R1, and it would say, I also have an entry that only goes through cluster 2.2.2.2, which is my own. So instead of discarding this particular advertisement because it came from the same cluster, it creates a second entry that says, I've got the best path, which is through the cluster, my own cluster, the cluster that I'm involved in, or I've got a backup path which goes through a different cluster. It just goes kind of like the AS path, where it has one extra AS to go through. Now it has one extra cluster to go through. So determining that this is its best path, this is what it advertises to its clients. Reflector 2 would advertise this NLRI towards R2, R3, and R4. Now, guess what? Reflector 2 turns around and does the exact same thing. It makes an advertisement towards reflector 1. And reflector 1 evaluates its own cluster ID versus the other advertised cluster ID. And it finds out that 1.1.1.1 is its preferred path because it's already in the cluster that it wants to go through. But it installs the backup path, which looks like 2.2.2.2, comma 1.1.1.1, in other words, the advertised cluster, then its own cluster, in order to get there. So reflector 1 will still advertise its preferred route through R2, 3, and 4, but have a backup route still installed should something go on between the connection between R1 and reflector 1. So now we've covered a lot in this particular nugget. Let's recap what we've learned or thought about here as we've gone through this journey. Route reflector rule of thumb, we're talking about 4 or more IBGP participating routers. This when we start considering when we should use route reflectors, and then we move into, well, should we use redundancy? How are we going to handle scale and stability? The IBGP formula was N times N-1 divided by 2. That way you can consider how many sessions will be established whenever we bring IBGP sessions up and get a full mesh scalability. And we learned about the benefits of using route reflectors in the first place. That's to get around that need for full mesh connectivity. Clustering and peering. We've seen how a cluster can come into play and change what we need to do. And we've also seen why we need to establish a peer between our route reflectors. Then we finally wrapped it up with understanding what the difference between the same or the different cluster would be. The big thing to keep in mind there is with a different cluster, meaning our route reflectors are using different clusters between each other, we would then have more routes installed in our BGP table, or more prefixes installed in our BGP table, and that would consume more CPU overhead. Keep that in mind when you start deploying your routers, and especially if you have a large enterprise with lots of networks being shared around through IBGP. Your devices are going to need that overhead in order to handle all of this route reflection and BGP best path calculation. So that's been understanding BGP route reflector design. I hope this has been informative for you, and I'd like to thank you for viewing. So we as an enterprise have deployed BGP. We've peered with either one service provider or multiple service providers to make it a multi-homed environment. We've also talked about how we could configure our network to manage or engineer outbound traffic as well as inbound traffic. Did it work? That's a big point. It's a big question to consider. The whole point that we were peering with our service provider in the first place was to share our prefixes. Now, how can we validate that the internet is reaching us through the most optimal path. There are some tools out there that we can use, and it's called the BGP Looking Glass. Let's explore some of the ways that you can validate your own BGP network deployments right now using real-world service provider routers. Let's check out the BGP Looking Glass. A major talking point about deploying BGP in your particular enterprise. Look at this topology that we have laid out here on the screen. This is the same topology that we used in the Nugget on route reflector design. We have our enterprise ASN 200, that's CBT Enterprise. Let's pretend for a moment that we were advertising the prefix 1.1.1.0/24. In the real world, this is a prefix used by Cloudflare. In fact, their security-based DNS services are the IP address 1.1.1.1. This is a very popular prefix that's deployed throughout BGP. But let's pretend for a moment that we were the ones advertising this prefix. How then do we know that our BGP deployment has proceeded and propagated through the internet successfully? How do we know that our clients are actually reaching us through the preferred paths that we want? And how do we know that our traffic is making its way there? One of the coolest things that we can look at is right here, talking point number 1, Looking Glass. What is Looking Glass? Looking Glass means we can actually telnet into a service provider's router publicly over the internet and look at their BGP tables, look at their route tables, and validate that we can actually reach our own prefix correctly. We can even use tools like ping or traceroute to see how we can get there. Here on the screen, I have brought up a list of looking glasses, most of which actually work, that you can actually use right now, and you can see who they're hosted by too. This is traceroute.org / and it's kind of got a pound symbol looking %20 glass. That way we can actually see the links of all of these providers. That's exactly what this is. These are enterprises and service providers that have opened up their services for anyone to look at. Immediately, I'm drawing my eye to CenturyLink AS209, which at the time of this recording, they are headquartered in Louisiana. That way we can actually telnet into CenturyLink and view their looking glass. Or sometimes they actually give us a web-based interface that we can interact with. If I click on CenturyLink right here, we see it takes me to CenturyLink.com/IP stats, and then it redirects, and we can actually see their whole MPLS backbone that they have across North America. Do you see this utility right here? We have Looking Glass. And from here, we can identify which server we want to source our traffic from. We validate which tool do we want to use. We can use ping, trace, or BGP. And then we can specify what destination it wants to go to. We could also specify a DNS lookup and try and run the BGP test towards a DNS lookup or a traceroute or a ping. So if I said something like mydomain.com, we could see how traffic sourced from CenturyLink's Arizona data center and their BGP environment makes its way to the DNS lookup that we choose right here. So we could specify our own domain and see how CenturyLink has their table laid out and how traffic is reaching our environment from CenturyLink. Very cool way that we can see how a service provider sees us. But there's other ways that you can do this too, and I wanted to bring this up. This is actually really, really fascinating. Looking back at the topology, my next talking point that we're going to cover is a Cisco-specific looking glass. This is where we can telnet into a Cisco device and look at its BGP table and figure out how does it think it's going to get to us. The vendor that we can do this with is Verizon in the UK. So let's telnet into one of Verizon's routers and actually see what routes does it know about and how does it reach specific prefixes. Again, we'll pretend we're looking up the 1.1.1.0/24 prefix. I'll bring up Secure CRT and you can telnet to that endpoint right now. There's no username or password required because it's very locked down about what you can do in the first place. And this is a device that runs a Cisco or Cisco-like environment. That's route-views.links.routeviews.org. So from here, I can give it the command show BGP IPv4 unicast summary. And there it is. There's the actual BGP table that we've learned on this particular device. We can see who our neighbors are, what autonomous system they're in, how many prefixes we received. Look at those numbers. Whoa! Over 800,000 prefixes, 834,548 prefixes. I don't see anything larger in this particular routing table, but we're talking a pretty big table of prefixes, right? That's monster. So we're going, okay, well, wait a minute. We want to see how did our 1.1.1.0/24 prefix reach this device in the UK? So I can give it the command show BGP IPv4 unicast, then I can specify the prefix 1.1.1.0/24. Press enter, and this is all of the advertised paths that it's learned about in getting to 1.1.1.0/24. Very, very cool. Now we can see within this autonomous system that this particular device is communicating in, which, by the way, this is Autonomous System 5439. We now know how Autonomous System 5439 is learning about the 1.1.1.0/24 prefix. We can see where aggregation points are coming in. We can see the AS paths. We can see the originating items as well as community strings that are being sent through each of these advertisements. And it's a really awesome way to see how our prefix made its way into Autonomous System 5439. Let's pick on one more, though, because here's the thing. You may try to reach one of these looking glass items and find out, wait a minute, they don't run Cisco products. For instance, let's pick on a service provider that runs Juniper products. Who is this? I'm talking about AT&T. AT&T has opened up one of their devices for a looking glass style environment, and it happens to run Juniper products. It wasn't always Juniper. They actually changed over to this particular device changed over to Juniper in relatively recent history. And I'm kind of sorry for the small font. This is route-server.ip.att.net. We're going to use Telnet one more time. That's port 23 to reach this device, and I'll click connect. Now this device is prompting me for a username and password, but look, it tells you the username and password to use right there, rviews. So if I type rviews, and then the same type again, rviews, now I'm logged in, and we can see this is using Junos 17.1 or a Juniper device. What we're really looking for here is show, and this happens. Sometimes it actually pauses this Telnet session because it's still trying to get connected here and it's still trying to wait. You got to wait for it. Okay, there it goes. It comes. It eventually shows the prompt move beyond the spacebar. I'll type show route protocol BGP and press enter. And this shows every single route that this device has learned about through BGP. And if you want to see a lot of routes, this is how you see a lot of routes. Pretty much every prefix on the internet is stored right here on this device. So if I could hit spacebar for forever until I eventually get to my prefix, it'll eventually get there. Or I could press up, we could do show route protocol BGP, and then type in the exact prefix here, which is 1.1.1.0/24. And now we can look at all of the paths or ways that we've learned about 1.1.1.0. So this is how we can look up the route table on a Juniper device. Similarly, I can say show BGP summary, and we could look at the BGP peer sessions. Look, this is pretty cool because it's got both IPv4 and IPv6 with show BGP summary. Not very many neighbor adjacencies here on this particular device because it's kind of peered only to a couple or a few peers, but it's learning about all of those prefixes. Pretty much every prefix on the internet is coming from these peers. So that's how we can actually use Looking Glass to validate how our traffic is reaching other service providers. They put it out there for us to see. We can telnet into these devices, look at the routing table, look at the BGP table, and look and see if our communities or our traffic engineering manipulations that we've tried to set have actually made its way through the internet. I hope this has been informative for you, and I'd like to thank you for viewing. So there you have it. Now you've seen that BGP can be a very deliberate protocol, and we can control exactly how it should behave within our enterprise network. We can control both outbound and inbound flows, but also leverage those communities so that we don't actually become a transit autonomous system ourselves. A very big and important factor for dual-homed situations. I hope this has been informative for you, and I'd like to thank you for viewing.